So today I will speak about diagrams of René Baire in the field of analysis. Just some elements about the life of René Baire. You could see on this slide that he was admitted to the École Polytechnique and the École Normale Supérieure. He chose the second one. He obtained the agrégation de mathématiques in 1895 and became a teacher the same year in the secondary school. And the next year, it's an important date because it's around this date of 1896 that his scientific career began. We have some elements that justify that point. For example, in his letters with Borel, we could see that Baire worked on some elements that will became his topic for his PhD thesis. And just 1 year after in 1897, he published a note, compte rendu à l'Académie des Sciences, about one small part of what will became his PhD thesis. He finished his PhD thesis in 1899, and you could see on this slide also that he became a professor at the Faculté des Sciences de Dijon in 1907. He replaced Charles Méret, and he stayed in this university until the end of his career. He finished to work in the academic sphere in 1914, because during all his life he had some illness problem, and he obtained a sick leave at this moment. So you could see that, in fact, his scientific career is really short, only almost 20 years, precisely 18. And after 1914, we have no work of Baire in mathematics. Just one note about the origin of one of his concepts, the concept of semi-continuity, but except this note, we have nothing new. And he was elected as a corresponding member of the French Academy of Science in 1922, especially thanks to the help of Émile Borel, who defended this promotion for him. Okay, so just to continue with some elements about the work of René Baire, and some biographical and bibliographical elements about him. The topic of his PhD dissertation was the field of the analysis, and especially he studied the functions of real variables, as you could see with the title of the PhD dissertation. He published several textbooks. You could see here 3 of them. One small one in 1905, and another one also entitled Leçons sur les fonctions discontinues, which was a course that he gave in the Collège de France in the Sherpeco just 1 year earlier, so in 1904. And he published also a big textbook about what is nowadays what we learn in the 3 first years at the university, so the license and the bachelor degree. This textbook was published in 1907 and in 1908 because you have 2 parts on this textbook. You have 2 volumes for it, we could maybe you could think that this textbook are not so important to study but we have several elements that testify the fact that in this textbook Baire show what he wants for the analysis. He proposed new ways to formalize these fields, especially he introduced some concepts that have already exist in some of the papers at the period, but he used them to rewriting the foundation of the analysis at different stages. So, for example, for the construction of the real numbers, but also to use set theory to formalize new statements about functions of real variables, things like that. And we have also a lot of many testimonies from several mathematicians like Jean de Demet or Abel Marijon, who was a mathematician at the beginning of his career, and then more an inspector of mathematics, so a supervisor for the educational field, educational sphere in France. And you could see, so for example, with Chandonnet, that he said the following thing: between Jordan's treatises and Bourbakis, there is only Baire's book. So these textbooks really mark people at this period. And last thing, last work in mathematics that I want to mention is it is the article of set theory by René Baire in the Encyclopedia of Pure and Applied Mathematical Science, the French version, because there is also a German one, which is in fact the original one. And in this article, he really translates the German article and rewrite a lot of different passages, because we could see that we have some marks. He put some stars on the part that he was writing himself, and almost the entire article contains some starts in front of the paragraph. So this is really more a synthesis by Baire than just a translation of the German articles. Okay, and just to precise one thing, keep in mind that set theory at this period is not exactly what we call nowadays set theory. Set theory had a broader meaning in the past than it does today. So, for example, on this slide, you could see that in the article of Baire, you have elements about in this theory. He put some elements about measure theory, but also some elements about topological results that you could see here with the notion of first category set and abstract set, which is a concept introduced by Fréchet and which correspond, in fact, to what we call nowadays a metric space, because you could see we could see here that he mentioned the property of the triangular inequality to introduce the notion of a distance, the space on the set. So this is really the beginning of a formalization by Fréchet of what we call nowadays a metric space. But the topic of today is not this article on about set theory. I will focus only on the diagrams that Baire drew on different work, and I will begin by some diagrams in his PhD thesis. You have different examples here. You could see so the three first one are at the beginning of his PhD thesis, but you could see also that it's not just in a specific part of his PhD thesis. You could find diagrams in all the sections of his PhD thesis. So if you observe the diagrams on the right part, so you could see that at the page, for example, 40, you have another diagrams, but you have also diagrams at the page 100, and the length of the PhD thesis is around 120 pages. So you have really several diagrams, and in every section you could find some of them. It's not just concentrated in one part at the beginning or at the end. You could find them in every part. And just some remarks about these diagrams. You could see also that in each of them you have a Cartesian coordinate system with two axes. So here, the x-axis and the y-axis. Even if some of them don't contain this explicitly this Cartesian coordinate systems, implicitly you have this. So if I take this one, the diagram 10 on the right, the interval AC correspond to the x-axis, and the interval AD correspond to the y-axis. So in some diagrams it didn't draw explicitly the line for the different axis, but implicitly you should keep in mind that if he folds of these diagrams like in this framework. Okay, most of these diagrams are relatively simple in the components. You have some rectangular, some straight lines, some trapezium, or and only this one on the left, so the diagram 12. This diagram is a little bit more sophisticated and complex, as you could see here. But in most of them, you have it's not easy to understand what it means without the text, but in the components of the diagrams stay at a simple level. That's just what I want to point out. Okay, what else? Sorry. And most of these diagrams represent with the Cartesian system, with the Cartesian coordinate system. This Cartesian coordinate system represents the domain of variation of two variables, because most of these diagrams concern a context about a function of two variables. So this is the case here for most of them. There is only one exception, the diagram 12 here, where the y-axis correspond really to the value, the image of the functions for different value of the x-axis. For the others, the value of the image of the function is not represented on the diagram. You have only the space, the domain of variation of the two variables. So as I said, we could observe that many diagrams in his PhD thesis appeared. I hope I convince you about this point. The diagrams always represent the Cartesian coordinate systems. They drew the domain of variation, as I said, and often the diagrams do not represent the image of function. So I said all of that. Another important point is the fact that some of these diagrams appeared also in another work of Baire, in his leçon sur les fonctions discontinues. You could see here on the first line of the diagrams on his lesson, and at the bottom of the diagram, the corresponding diagrams in his PhD thesis. So you have really the same sequence of diagrams and almost the same diagrams also, but you could see one difference. So for example, for the diagrams at the middle, you could see that you have two diagrams in his PhD thesis. In his PhD thesis, the two diagrams are really in this disposition. So you have diagram 6 at the right of the diagrams 7 on the page. And in his lesson, the diagram 6 disappear. So I will explain why in a few moments. And you have the same for the diagrams on the right, as you could see. But you could see that he really used the same diagrams, and it seems that that kind of diagrams have a really important role for him because his lessons are published 6 years later. So even 6 years later, he wants to maintain this way to present his arguments and not to use, for example, some algebraic formula. So I will explain in more details that in a few moments. But in his lesson, you have another kind of diagrams also. You have diagrams with one dimension, like in the left of the slides. Even if you have an exception here at the middle with a diagram of 2 dimensions, but most of the diagrams, in fact, in his lesson are with 1 dimension only. This is a big difference with his PhD thesis, and I will explain that point also. But again, you could observe that we have many diagrams, so it seems that Baire really wants to employ that kind of way to communicate some results. Okay. His lesson on discontinuous functions deal with the same subjects as his thesis, hence the use of common diagrams that I show you on this slide here. You have the same sequence, however, contrary to his thesis, Baire wrote his lesson very differently. Several chapters are devoted solely to introducing theoretical notions and concepts that he would use later on. In his thesis, definitions appear rather throughout the resolution of mathematical problems, during the different sections, and it's not the case in his lesson. So just to show you that point, you could see that here on the right you have the table of contents of his lesson, and on the left, it depends. In my right, you have the table of contents of his lesson, and on the left, you have the table of contents of his PhD thesis. And in the table of content of his lesson, you could see 2 chapters are really independent of the rest of his work. So the chapter 2 and the chapter 3 that deal with some concept about set theory. And in this chapter, you have only diagrams with 1 dimension. So this is the big difference, because the content of these 2 chapters are really split in different sections in his PhD thesis. So you have not the same structure, the same organization. And if Baire used only diagrams of 1 dimension, is just because one paradigmatic example of what is a well-ordered set is a real number, the set of real numbers. And so each time that he introduced a property about, so when he introduced the definition of what is a well-ordered set, and when he introduced some property about that kind of sets, he verified that the set of real numbers has this property, and he used these diagrams. And so the diagrams of 1 dimension are really a different role than the diagrams of 2 dimension, because it's more an example of a particular example of what he introduced in in the text with more theoretical concept, then it's more an illustration than really something that he used to develop the property that he introduced in this two chapter. Okay. Furthermore, there's lesson as totally around the following mathematical problem. So the problem which consists to find all the discontinuous function which can be represented by the limit of a sequence of continuous function. You have the quotation in the introduction of his lesson that testify really this point. And in his thesis, this is not the case. This mathematical problem is just one of the problem he studied. You have several other ones. So I put here, you have, in particular, you have another problem about a function of two variables. As you could see, it's the problem entitled 1, a function of two variables x and y being submitted the condition to be continuous with respect to each of them, so separately. The values which it takes on any line from a function of one variable, which may be discontinuous, and Baire proposed to determine its nature and to find which conditions force the fact that the function will be discontinuous. And this problem, Baire takes this problem in relation to the problem that he introduced later in his lesson, so the problem of a representation as a sequence of continuous function. That is the problem 2 here on the quotation. But the two problems have the same importance in his PhD thesis. It's not the case in his lesson. Only the second one is really important for him. The first one is just one step at the beginning of his lesson to show that in fact if you solve this problem, you could solve also the problem for a function of two variables. But he used also this problem, as we will see in a moment, to develop some argument, but he didn't study in detail this problem as he could do in his PhD thesis. And we could see that he really studied and that this problem about a function of two variables have an important role in his mind in his PhD thesis, with the fact that Baire introduced several versions of this problem. So here you have different examples. The problem 1 and the problem 2 correspond to the previous problem here, but you fix the line where you consider your function of one variable. So here is on the line where y is equal to x, and here you consider the line y equal to 0. And you have also another version, for example, here that he entitled the problem 3, which is a more general version of the problem 2, where the assumption on the function are weaker than in the problem 2. You consider only the fact that the function of two variables is continuous with respect to y only on some straight line parallel to the axis, to the x-axis, but not on all the lines. But you suppose, of course, that the set of the lines where the function is continuous with respect to the second variable is dense with respect to the set of all lines parallel to OX. So this is an important condition, but you could see that this is a weaker version than the problem 2. Okay. And so, in fact, because in his PhD thesis you have really two different problems that has the same importance. So the problem about the function of two variables and the problem about the representation as a sequence of continuous function, you will have because you have several versions of the problem about the function of two variables, like for example the problem 1 here, where you fix the straight line y equal x, and here the straight line y equals 0. You will have different diagrams. So the diagram 6 here at the bottom correspond to the diagrams in the case where you consider the straight line y equal x, because it's the diagonal of the square, and in the diagram 7 at the bottom correspond to the case where you consider the straight line y equals 0. And he put these two diagrams in the same in relation, because he wants to justify the fact that it's not really important which line you fix to obtain a function of one variable. Never mind which line you will choose, you will have always the same steps in the demonstration, in the proof, and so he showed us in different case here, and he put these two diagrams to show the fact that we are really the same step, and so it's not really important, and we could in fact just restrain to one case, and it is sufficient. So one reason why the second diagrams disappear in his lesson, I think, is due to the fact that Lebesgue wants to focus. There. You said Lebesgue. Oh, sorry. Because Baire wanted only to focus on one problem, to simplify the course that he gave, and to help students to deal with the content that he present to them, because we have some testimonies that students complain about the difficulty of the course. Even Baire said that in his letter. There was only one student, Arnaud d'Anjois, who succeeded to follow really the course, and it's not a surprising thing, because it was him who compiled the course to publish that in a textbook. even if Baire read what Danjois note during the course and make some correction, but this is him that helped him to do this work. Okay. And just so in the next part of the talk, I will focus mainly on this sequence of diagrams. So these three diagrams especially. And we could see that this sequence of diagrams is really important for Baire, because even in his later, we could see these diagrams in another form a little bit, because here Baire suppose only the continuity on the first variables, or on the x variables, not on the y variables. So you have diagrams that you should make a rotation of the diagram if you really want to have the same diagrams here. So just turn to have this exact. But here is a letter of Baire to Borel, and you could see that you have exactly the same diagrams as in his PhD thesis or in his lesson. So this is really a redundant diagram and a redundant problem about how to about the problem of the function of the variables that I evoked just before. Okay, so just to give you some contextual elements about this diagram, and to try to explain you why he chose to use that way to present his arguments. I will use my words. So you have the quotation. I will just illustrate what it means behind this. So you could take just a function of a discontinuous function with one discontinuity. So for example, you could take the function tangent on the interval No.
No, in fact, we saw quite well with the camera, Karine.
Okay.
If we make it
Larger, okay.
larger, yes, it's okay. The focus is also okay, so yeah, thank you.
Thank you.
So if we take the function tangent on the interval minus p divided by 2 and p, you will have the following function. So you have the discontinuity p divided by 2, and so what we want is to construct a sequence of continuous functions that will tend to this this function here. So the idea is just to consider interval around this discontinuous points, and to take for every term of the function the same value of the initial function, but on the other part you will consider a linear function. So for example, for f1 you could take here p divided by 2 minus 1 divided by 10. So here is the interval that I will consider along the discontinuous point. So p divided by 2 minus 1 divided by 10 divided by 2 plus 1 divided by 10. And on this on the rest of the interval of minus p divided by 2 and until p divided by 2 minus 1 divided by 10, and on the other interval p divided by 2 plus 1 divided by 10 to p.
Just 1 second. You mean from 0 to p, because you said minus p over 2,
yeah.
But on the other hand, you finish at 0 of the function. On one side, you said p over 2 plus 1 times t pi.
Yeah.
And on the other side, you said minus p
divided by 2.
Where the function is discontinuous.
Yeah, but as you consider only your function on this interval, it's just an asymptote, so you have not really a discontinuity if you try to draw the part of the diagram. So it's not so important what we will have on this point here. You could exclude the extreme of the interval. You will see when I will write the expression.
I was just noticing that what you do is not symmetrical in the sense that to the right you go to a 0 on the function, and to the left.
Maybe we could just we just will exclude this. And I forget one point. You should fix the value of this function on the p divided by 2. So, for example, I will take 0 on this point to fix it. So the function is the x equal x if is different p divided by 2 and it's equal to 0 it's equal to p divided by 2. Okay, and on this part the function f1 will be the same function on this whole, the same so the whole here. And as I said, we will change the nature of the function on this interval here, small interval. We will consider linear variation. So if you take the value of f on this point, p divided by 2 minus 1 by 10, and you draw the line between these 2 points. So continues, it's just by drawing. And you do the same on this side. So you have 2 straight lines here. And the other part, exactly the same definition as f. And so you could really write the expression f1. This is so it's so okay. I will not just like that. 2 2 1. So this is just an expression that I will express in details. Start flat space, and if it's is minus p divided 2 minus 1 and 10, and p divided 2, so it's small. But you just consider this interval here for a, this interval here for B. It's two P2 plus 1 by. So you have three cases for the definition of F1 with three different subparts of your initial interval. Okay, and you could really write this expression of A here on F1. So you just Baire proves how we could obtain this expression in this lesson. It's just you should just solve a system. It's not so complicated. So you take the value here, and you multiply by x minus t, and then divided by 2 plus 1 divided by 10. Plus P2 times P2 minus x, and all this expression will multiply that by the opposite of the length of the interval, so here by 10.
Didn't you say that you define f of pi over 2 as 0?
Yeah. That's great.
So
yeah. Yeah, but yeah, so you have just this part but it's the general expression. If you take another value for this point, you will have this expression. That's why I wrote this in general. So you have this, and you could write something equivalent for P. So you just exchange, and here you put plus. It's not really difficult, but you could really express the algebraic expression of this function. So this is the first term of the sequence, and you could construct another term, so the function f2 of x, just by considering a smaller interval. So then we will take here p2 minus 1 divided by 100, and the same pi divided by 2 plus 1 divided by 1. And on this interval, you do exactly the same. You consider exactly the same definition and the linear variation and parts. So for f2, you will have also an expression like that, 3 cases, and you could write the definition, and you could construct like this a sequence of function f n that will turn to your function f, but this different function f1, f2, and so on and so forth have the property to be continuous, all of them, thanks to this trick here. So this is the method that Baire introduced in this lesson for the case of one discontinuity. But what he wants to do is to consider the case of a general discontinuous function. So you could have an infinite number of discontinuities. So you want to generalize this method to the case of an infinite number.
Any kind of infinite number?
He wants, but he will limit himself to a countable infinite number. But I will explain this. What is interesting is to generalize this method, he will use the diagrams and not a construction like this. And we will see why he there didn't give some element to explain that. But if we follow what he said with the diagrams, and if we try to do that with this analytical method, we could see what they want to avoid. I can try to explain now this up. So if you have a function of with two discontinuous points, I could take the same function, so the function Panthéon, but I will take the next part. I will take an interval a little bit more bigger. So I will go from minus p divided by 2 to 3 pi. So here you will have two discontinuous points.
If you write something on the blackboard, we see absolutely nothing.
Oh.
Because the camera is fixed on the other side. Yeah, thank you. And the focus, yes, is well made. So perfect. Thanks.
Thank you. Okay, here you have two discontinuous points. And in fact, you could really use again this method. You will have no problem. So in this case, we could the function, but your function here F1 will have so 5 cases for the definition, and it's exactly the same for this. And in fact, it's works for this function because the two discontinuous points here are not so close. Because if you have two close points here, you should choose an interval that is sufficiently small to be able to make this construction. So it's work if you have an infinite number of discontinuous points, but if you take a countable number of discontinuity, it becomes very more difficult to do that. So if you take the set of discontinuous points, if you take, so for example, if you take D equals to a set of rational number, it becomes really a problem to solve this, because you could not employ this method, because the set of rational number is dense real numbers, so you could not find a distance between each discontinuous point that will allow you to do this construction. So you have really a problem, and it's all the challenge of Baire to solve this case. But even for more simple case, so if you take, for example, that one, so 1 1 divided 1/2, 1/3, 1/3, 1 divided by n, and so on and so forth. So it's an interval set. Here, it's not a dense set of numbers. So you have not this problem. But if you study the distance between two terms, it tends to 0, because if you do 1 divided by n plus 1 minus 1 divided by n, it's equal to 1 divided by n plus 1 multiplied by n, and this tends to 0. So you could not fix an increment, a step, an increment that is sufficiently small for each discontinuous point. So you have to change the increment during your process. So if you want to do that, you should introduce something that is usual today, that is in fact a sequence of a sequence. So so here you could consider in fact the sequence alpha n, which is equal to 1 divided by 10 over n, and this is the increment to construct in fact your different term of your sequence. So f1 is just for alpha 1, and f2 is for 2, and so on and so forth, and alpha n tend to 0, so there is no problem. But here you could not have something like that. You should have for each point a specific increment. So you will have a sequence of a sequence, and for there, this concept seems not to be so easily to introduce and to consider. So I don't know if it's just for pedagogical reason, or if you really have some complaints about that kind of concept. So he had to find a trick to avoid this concept and to succeed to construct this sequence without using that, and so without using this method, but had to use that. Okay. So Berthod is the sequence of diagrams that I show you. Okay, he introduced a first proposition that I called transformational proposition that allow him to transform the case of where you have a sequence of continuous function in the case of a representation by a function of two variables. So as he said, finding a sequence of continuous function whose limit is a function fx defined on the segment AB is absolutely equivalent to finding a function of two variables which reduce to fx, and with some assumption on that function. You could read that on the quotation. And he proposed a construction to do that. It's what this diagrams illustrates. I will not enter into detail because I have no time, unfortunately, but believe me. And thanks to that transformational function, he succeeded to extend the previous result. What we could see firstly, it's that he deal with the case of one discontinuous point again. He used just one more assumption, is the fact that if you find a function of two variables that represent your function as in the transformational proposition, you could choose an arbitrary value on the border of the rectangular domain here. You could choose what you want. And thanks to that, the problem of one discontinuous point in C will be just easily solved, because it's just to, if you have, if you could transform your sequence of continuous function as a function of two variables on the segment AC and the same on this segment CB, you could just stuck the two definition to obtain a definition of a function of two variables on the segment AB, because you could choose an arbitrary value on the straight line C1. It's not a problem thanks to this assumption that he proves. So you will have the proof very easily thanks to this diagrammatic reasoning, I will say. And here is for one discontinuous point, but he deals with a countable number of discontinuous points, and especially with that one, for the set of 1 divided by 2, and so on and so forth, and 1 divided by n, so on and so forth. So a countable set of discontinuous points that is not dense in the real numbers, in the set of real numbers. So if you have this, you could so obtain your result just by glue the definition on the different trapezium here, because in a trapezium you will have only a finite number of discontinuous points. So you just repeat the previous construction for one discontinuous point, and you will obtain that for a finite number. And here, thanks to that property, you could extend to a countable number. Okay. So yeah, if I show you that, is to illustrate different thing and different statement that Baire claims in his in the introduction of his book, or in some section of different chapter. So for example, you could say in a section that geometry, trigonometry, and analytic geometry use arithmetic and analysis to study geometric properties. But conversely, geometry is useful for analysis in several ways. And he had, it provides simple representation of analytical results, often also a quick and a convenient language. And here you have also this idea of mutual borrowings between analysis and geometry. And I think that Baire has in mind that this diagram when he could wrote this passage. Okay. Yes, I will pass that. First of that. So just to conclude, behind this sequence of diagrams, we can find some of Baire's epistemological choice. I believe that Baire used this method of presentation for his argument in order to obtain a constructive method for establishing a priori all the terms of the sequence of continuous functions. Because if you use method that I show you on the board, you could not express the expression of every terms of the sequence, because you should introduce this sequence of sequence if you want to do that. And Baire seems to not want that, or just didn't see that possibility. Another point is the fact that this case study shows that it is relevant to consider not only diagrams for themselves, solely in history of mathematics, but also in a set of several diagrams. So in this sequence, for example, to understand their role. Several articles have already shown this point, especially in the case of geometry. I have in mind some works for the case of Euclidean diagrams, for example, but this is less true in analysis. And I think also that this case study is a good example for studying the fruitfulness of a change in the framework of mathematical programs. So here you have the example of a change from something that is really in an analytical framework. You consider a sequence of functions, continuous function, and you transform that in a more diagrammatic language to solve the problem. So you have things like that, and some authors testify of this of the fruitfulness of a change in the framework for the case of algebra. I have in mind an article of Jessica Carter in the case of combinatory, but also an article of Tapaden for the case of Riemann geometry that point out about that. But here, I think it's a good example in the case of analysis that it is really less studied than some example in algebra, topology, or geometry. Thank you.
Maybe you have a question for Thomas?
If anybody wants to begin, no problem. I mean, I was struck when you started to write the analytic formulation, because when you look at the diagram, it's absolutely obvious that there is an analytic expression. You can write it if you want, but clearly writing the analytic expression does not add to the argument. So I came to the idea that, at least in some cases that you have presented, the diagram acts like a way of writing many analytic expressions in a very compact way. So it's a kind of a new way of writing functions that spares us all the analytic details that add nothing. So would you agree that, at least in some cases, the diagrams write many functions of this kind in a compact way, where everybody would be able to write analytically what this refers to, but this expression is completely dispensable?
Yeah, I agree, because when Baire drew, so it's a little bit slow. This diagram here to establish the equivalence between the sequence of a continuous function and the representation by a function of two variables. So he used that kind of trick of a linear variation between the different straight line that he put on the diagram, and when he said what is the expression of the linear variation, he said it's just one example. We could take one, for example, that expression, but there is many others that will work also, and I choose that one because it's simple, but I could choose other ones and we will have the same result. It's not a problem. So I agree that it is really something that you have in mind, and we could see also that when he used the assumption that it's not important what is the value of your function of two variables on the border of the domain of definition, because he used also some continuous variation, and he said I choose the linear variation, but I could choose any continuous variation. It will not be a problem. I will obtain the same result. So he has really that in mind, and by the terminology, the terms that they employ, I think you are right about the fact that this diagram represents a different function, because you really use the words represent. He said the function of the variables represent the function of one variables in the same meaning for him as he used the same word for the case of the function of the variables and for the case of a series of continuous functions. So in one case, you have really something that seems to represent a function, because you could write the algebraic expression next to a sum. And in the case of the diagram, it doesn't seem so obvious if you just read like that. But if you use the same word, I think you have this, the idea that you have the same phenomenon here.
Okay, Mario has a question. Yeah. So since I have a follow-up question, but let other people speak.
Yes, thank you, Thomas, for your talk. I am interested to know if there is a posterity of this kind of method initiated by Baire about diagrams, or was he an isolated case?
So I maybe I will not answer exactly to your question, because I don't find another mathematician that use that kind of method for the moment. But what I see, it's the fact that this method struck some mathematicians in the period of Baire. Is especially the case of Jules Tannery. So Jules Tannery wrote a review of his PhD thesis and of his lesson. And in fact, we could see an evolution in the position of Tannery about the use of diagrams or figure in analysis between his review before his review and after his review, because we have this book, Introduction à la théorie des fonctions d'une variable, a famous book of Jules Tannery. And in the first edition, Jules Tannery really said that you should not use geometric or spatial arguments in analysis. You should only use algebraic formula and really express everything like that. And in the second edition that I put the introduction here, you could see that his position evolved. He said, for example, that profiter des facilités qu'offre le langage géométrique at the end of the quotation here. Sorry, it's a big quotation. I should just cut some parts, but you could see really in this passage that for him, diagrams now could be used in analysis perfectly, and it's a good way to present an argument. And in this edition, we have several references to Baire works, so we could really establish some lineage between both of them. So maybe I should make more research on this side, but for the moment I have not explicit use of their diagrams for the development analysis. Just some commentary of other mathematicians, like Cité.
Okay, thank you very much.
Yes, Paul-Emmanuel.
Yes, thank you for your presentation, Thomas. I have one question about the part of your talk when you compare the two table of contents between the one of the PhD and the one of the leçon sur les discontinuités, sur les fonctions discontinues. When you compare the two table of contents, you said that in the leçon we see two chapters, more theoretical, if I can say, comparing to the table of content of the PhD, where we can find the same contents but more mixed inside of other chapter. Is that?
Yeah, exactly.
And I just want to ask if the fact that Baire choose to make these two chapters separately is linked to his first publication or his first book of 1905, Théorie des nombres irrationnels, des limites et de la continuité. We find exactly the same thing, and perhaps because he published that after the PhD, he chose to take the two chapter and put it in his leçon.
Which book do you say?
Yeah, so
in,
the
1905.
the book between yes, but in fact the book between the PhD and this one.
Okay. In fact, book is not about the same topic. It's absolutely another thing. Baire didn't use what he present in this book in his leçon sur les fonctions discontinues. He used that in his thesis book on the leçon sur les théories générales de l'analyse, but he didn't use that in this lesson. So there is no clues about the fact that this book could change his mind on how to organize his argument at this level. I think it's really more some pedagogical reason, and the fact that also at the same time, I think it's just three years after his leçon, so in 1908, he published also a memoir sur les fonctions discontinues. It is the title. And so we could see that the main topic of his research became that problem of finding a representation of a function as a sequence of as the limit of a sequence of continuous functions. And so that's why I think he rewriting what he have done in his PhD thesis around this problem and use that to pursue his research on that topic.
Okay. Okay, thank you.
Thank you for your question. Of March or Emmanuel. Don't know. Oh, okay. Go on. Well, Emmanuel, if you have another one.
But I know Karin has also another question, so perhaps Karin, you can, and after.
Yeah, I find the corpus is very interesting because you can distinguish in the view between the kind of innovation that was introduced for his work in his PhD and how these innovations changed in relation to the fact that he was teaching. So I think it would be interesting to find out whether there are notes that some students took during these lecture courses. Perhaps Danjois would be.
I think it's the version published more or less because there's said in some letters that he make really small correction.
Okay.
About
the letters, I assume that some people publish them.
Yeah.
But it would be important to go back to the manuscripts to check the diagrams in the letters. But I think there is really something that would be interesting because clearly modes of expression that do not entail thousands of formulas, but that are more compact, are useful for teaching, but clearly he already uses them in his PhD, so before he teaches. So I think it would be interesting to try to find out which transformation the diagrams have in relation to the fact that he started to teach at some point, because there is evidence that he taught these topics. So it's more a suggestion.
Thank you. Suggestion. There is a question of François Le.
Yes, thank you. It's actually a kind of a mix between a question and a reflection that I'm having. But so at the very end of your talk, you mentioned this idea of change of frameworks.
Yeah.
And you mentioned other examples, and for instance, the case of Riemann.
Yeah.
And I just wanted I would like you to maybe know more about what you have in mind about this. Let me just explain what I mean. For instance, I think that in Riemann, you have also problems coming from analysis, but you have the introduction of a new object, namely Riemann surfaces, right? To deal with problems of analysis. But also you have other examples in the history of math where, for instance, to understand Riemann, people geometrize things as well, but they use objects, techniques, results coming from different parts and that already exist, namely projective geometry. And they use objects, techniques, and so on that already exist and that are part of an existing discipline, if you wish. And here in your case of Baire, but also of Tannery and so on, when you have comments about the benefits that geometry can bring to analysis and so on. And I have the feeling that we are not faced with the same kinds of disciplinary interfaces, if you wish. So I just wanted to know if you have more on this kind of issues in your mind or not.
Okay. So just to be precise, it's just an example of that I take from Tapaden, who wrote an article about the fruitfulness of a change of framework. So I say Riemann geometry, but more precisely, in fact, is more in complex analysis by using, in fact, Riemann surfaces, as you said. So I have not in mind all the arguments, so I could not now tell you much more about that. But maybe you have absolutely right. It's not exactly the same thing that happened in my case and in the case of Tapadon. Maybe the argument of Tapadon is not really a good one. I don't know. If I remember well, even Tapadon didn't develop so much what he have in mind with behind this idea of a fruitfulness of a change between the train in complex analysis of Cauchy or from Weierstrass in opposition or in relation with the train of Riemann and the framework that he introduced for the complex analysis. I could not tell you much more about that.
But, yeah, but actually, my point was really, do you see the kind of geometry that Baire uses actually as already part of analysis, or are really something on its own?
Okay, for that I could answer. Yeah, for Baire, it's really two different fields, but you have a connection between both of them, and he really insists on that. You could see I go really quickly on that part, but he insists on the mutual borrowings between these two fields, and for him, you should not maintain a strong border between these two fields. You should really use the overlap between these two fields to develop new statements, new theorems, like in this case study, for example. But in his textbooks about leçons sur les théories générales de l'analyse, we could really see that for him, geometry and analysis are two separate fields in itself. Because when he, even for the object of a curve, he considers a curve analytically and a curve geometrically, and for him it's not exactly the same object, it's just a different point of view on two different objects, I could say.
Okay, I don't want to be too long, so thank you.
So I think we can close this session. So thank you for coming. And the next session, I don't remember.
It's
The 13.
Yes.
13.
about content.
No, it's
No, it's Ken Manders.
Oh, yeah, sorry. It's when it's the session on yeah, sorry.
Oh, you got a tip. Instead, please, go. Please.
So yes, so Ken Manders and Karine and Bruno.
If we are
Thank you for
still
coming.
alive by mid-February, which is a bit determined. Thanks a lot.
Thank you.
Thank you, Thomas. Bye bye.
Ouais.
Thomas,
Oui.
sorry. Sauf si tu as des choses à faire, est-ce que je peux juste reformuler ce que je voulais te poser comme
Oui.
question? C'est juste que je voulais pas accaparer la discussion et comme il était l'heure. Si tu veux, ce que je voulais dire, c'est que je suis bien d'accord avec toi et c'est clair que si tu veux, tu vois, que Baire dit bien que les courbes, les figures, tout ça, c'est du côté de la géométrie, les fonctions, machin, c'est du côté de l'analyse. Mais ma question, c'était un petit peu, est-ce qu'il y a vraiment, tu vois, des résultats ou quelque chose euh, qui serait obtenu de la géométrie, mais qui viendrait de travaux décorrélés de l'analyse? Tu vois, c'est quand même une manipulation de type de diagramme, de type de choses dont on a l'impression qu'ils sont intrinsèques, tu vois, qui viennent de l'analyse. C'est pas comme si on
Oui.
avait des
Oui.
résultats sur les courbes qui viendraient, par exemple, des travaux, je sais pas, tu vois, de Plucker sur les courbes algébriques.
Oui.
Donc, c'est pour ça, tu vois, je suis
Oui.
d'accord
Oui.
qu'il y a vraiment une distinction disciplinaire, mais je me demande si c'est quand même pas une partie de la géométrie, enfin, tu vois, qui est en fait de fait liée à l'analyse.
Oui. Alors, juste ça, pour répondre, il y a le phénomène inverse, c'est-à-dire que, par exemple, il s'intéresse à la longueur d'un arc ou à des...
Désolé de te couper, Thomas, mais en fait, on te voit pas sur la caméra.
Ouais.
Donc peut-être que là, pour la discussion, ce serait... Désolé.
Euh, oui, oui, il calcule la longueur d'un arc de courbe à un moment. Il propose, donc c'est une formule déjà bien connue, et il propose juste une démonstration. Et dans la façon dont il fait la démonstration, il va pas le faire avec des arguments de géométrie infinitésimale. Il va vraiment proposer en fait un point de vue beaucoup plus analytique en introduisant vraiment des éléments de calcul différentiel pour proposer sa preuve. Donc c'est un peu comme ce que peut faire Jordan. Et donc du coup, il déduit quand même des résultats géométriques à partir d'un cadre purement analytique dans le cadre de ces courbes-là. Donc,
Ça oui, mais du coup, tu es dans l'autre sens.
absolument un autre point de son travail que j'ai pas du tout présenté là, mais du coup, tu as quand même ce phénomène-là dans ses travaux, par exemple. Là, j'ai parlé du cas du calcul de la longueur d'un arc, mais il y a aussi des propositions sur les surfaces, le calcul des aires de surface ou sur des volumes
Oui,
où tu as ce genre de phénomène.
mais là, du coup, tu es dans l'autre sens, c'est-à-dire
Oui,
que
c'est dans l'autre sens. Oui, oui, je suis d'accord. Euh, du coup, vraiment de l'analyse, du coup,
en fait,
utiliser un cadre géométrique pour développer des résultats.
disons, est-ce que, enfin,
euh,
tu vois, je suis comment dire, je suis absolument certain, et j'ai des exemples en tête, où l'intuition géométrique, etc., tu vois, permet de trouver les résultats en analyse, tu vois,
oui,
grâce au diagramme. Mais ma question, c'est est-ce que cette intuition géométrique, elle est développée par ces gens uniquement sur une géométrie qui est qui est elle-même, de toute façon, tourne toujours autour de ces mêmes sujets d'analyse, de séries, de fonctions, etc. Ou est-ce que ça peut venir aussi d'une partie d'un entraînement, d'un savoir qu'ils ont acquis dans des cours de géométrie pure, dans des cours de géométrie analytique, enfin, tu vois, qui vient
mm,
d'ailleurs. Ou est-ce que, en fait, c'est que de la, c'est leur entraînement, en fait, de l'utilisation des diagrammes en analyse de toute façon. Je sais pas si j'arrive à me faire
oui,
comprendre, en
oui.
fait.
Pour le cas de Baire, je dirais qu'il n'y a pas vraiment ce phénomène-là, et c'est vrai, il n'y a pas vraiment de pratique géométrique qui l'influence dans le cadre de la géométrie, parce que on a plus, enfin, il fait plusieurs candidatures pour essayer d'obtenir des chaires dans des facs parisiennes. Et il dit que bien qu'il n'a pas du tout étudié en fait le champ de l'analyse et les travaux en analyse de sa période, il pourrait s'y mettre pour donner des cours dans ce cadre-là. Donc, à travers ce type de témoignage, on a l'impression quand même que ses connaissances en géométrie sont très minces et qu'il n'est pas du tout familier, par exemple, du type d'auteur que tu peux étudier. Lui, ses références, c'est vraiment plutôt l'école d'analyse italienne, donc Dini en particulier, et Volterra. Même chez Volterra, il y a quand même des choses géométriques pour le coup. Donc peut-être que de ce côté-là, il y a des choses, mais chez Baire, ça transparaît pas forcément. Après, il a peut-être pas forcément eu le temps. Comme j'ai dit, sa carrière scientifique elle est très courte. Donc
Oui.
finalement, il n'a pas pu énormément développer tous ces résultats qu'il a pu entretenir. Je sais qu'il a fait la démonstration de la preuve enfin, il a commencé une démonstration de la preuve que Rn est isomorphe à Rp si et seulement si les deux dimensions sont égales. Donc ça, il essaye de démontrer ce théorème-là. Il fait une ébauche de preuve. Brouwer la reprendra un peu après. Donc peut-être qu'à ce moment-là, il y a des influences qui pourraient être intéressantes pour répondre à ta question.
Mm.
Mais là,
Mais-
sur le
ouais.
moment, je n'ai pas regardé ce
Non,
texte.
non, mais à vrai dire, moi, je pense qu'il n'y en a pas.
D'accord.
Mais ce que je pense, en fait, c'est ce que enfin, mon
Après,
point,
celle-là, c'est pour le cas de Baire. Pour
Ouais,
le
ouais,
cas
ouais.
de Lebec, je serais beaucoup moins formel, par exemple.
Bah, je suis pas sûr non plus, mais si tu veux, bon, on pourra en discuter, je pense, à un autre moment, mais c'est aussi un peu une suggestion. Je pense que c'est pas très bien fait, en fait, les gens qui discutent justement les apports de la géométrie en analyse, tu vois, que c'est pas bien délimité, en fait, de quelle géométrie on parle et
Oui.
d'où est-ce qu'elle vient, à quoi elle se raccroche, comment elle se le développe, est-ce qu'elle est en autonomie avec d'autres morceaux de la géométrie, etc. Est-ce qu'elle est développée par d'autres personnes que les analystes, en fait, et tout. Et je pense que c'est intéressant de regarder ça, tu vois, quand on fait justement toutes les questions d'interface disciplinaire, c'est vraiment de circonscrire en fait très précisément toutes ces
Mhm.
choses-là. Mais
Oui, je suis
voilà,
d'accord.
c'est tout.
Merci pour la remarque. Je vais essayer de
Bon.
regarder
Je
ça.
vais filer parce qu'il est 4
Ouais,
heures.
merci pour ta remarque.
Merci, salut.